Now radiation force on perfect reflecting sphere. You can see the sphere with radius r and this parallel beam of radiation with intensity is I is striking this surface. It can exert the force during the reflection. To know the force, let me remind the formula of the radiation force on reflecting surface. If it is the perfect reflecting surface and this is the radiation of intensity I, if it strikes this surface with an angle theta with this normal of the surface and reflecting with the same angle, and the force exerted by this radiation on this surface already we have written 2IA cos square theta by C. That is the radiation force on perfect reflecting surface. What is the direction of the force experienced by this surface? Always perpendicular to its surface in opposite direction to this normal. So this is the direction of force. So already we derived this 2IA cos square theta by C. A theta is angle made by the direction of radiation with normal of the surface. But here you can see these are the light rays which strikes this surface with different angles. So that is why we cannot apply that formula directly for this entire sphere. And this sphere, this radiation can cover up to this half of the portion only, like this. This portion is illuminated with the radiation, and the direction of this radiation with normal make different angles. So these photons will hit this surface, this half of the part of the sphere with different angles. So that is why you cannot write this F equal to 2IA cos square theta by C. We should not take this area as 2IA means we should not take 2 pi r square, because theta is not same for all the photons which are striking this surface. So that is why we should divide this sphere into small strips. So I am going to divide this. If it is the one of the circular strips, this is the strip, circular strip. This is the circular strip. You can see if it is the center of the strip, and this is the center of the sphere O, and this is the center of the strip O dash. Join these two with a straight line, and this is what radius of the sphere, and this is what the radius of circular strip. You can see here we have a triangle. This side is R, this side is what? Small r, and this is theta. You can write directly from this. If it is theta, angle between these two sides is theta, then from this triangle sin theta equal to small r by capital R. So small r is equal to, I am writing directly, small r equal to r sin theta. What is this small r? Radius of this circular strip, right? Now first I will write the force experienced by this circular strip due to this radiation. You can see here this radiation is striking this circular strip surface here at this portion. So here intensity of radiation is I, and here you can draw the normal to this. This is the direction of this area vector dA, and angle between these two is theta here. This is theta, this is also same theta, same line, and this is the horizontal line. Clear? Now the force experienced by this strip, this part of the strip, I will write first dF is equal to, based on that formula, 2IA, A means area of this strip, dA cos square theta by C. What is the dA? Area of this strip. Strip area you can write. So I will write here dA equal to its length 2 pi r into thickness dr. Thickness. Let us say thickness of this strip is the dr. We can write the thickness of this strip like this. So if I join that edge of this edge of the strip with the two lines from the center of the sphere. This angle is d theta, this is r, this is the strip, thickness is dr. So from this arc you can write dr is equal to r d theta, that is the thickness of the strip. So area of the strip is 2 pi, this small r is r sin theta, and dr, thickness of the strip, is r d theta. That is the area of this circular strip. So force experienced by that strip is 2I 2 pi r. So you can write 2 pi r square, r into r square, sin theta into cos square theta by c. That is the force experienced by only the strip, but force due to all the strips. So to know that, first what is the direction of force experienced by this part of the strip? So it is always based on this diagram, it is always against this direction of the normal. So this is the direction of the normal to this strip, and it passes through the center of the sphere. So the force on this strip at this part is like this, dF. It passes through the center like this. If it is theta, this angle also theta. You can resolve this dF into components. Its component in this direction dF cos theta, in this direction dF sin theta. For every strip, every part of this strip, there is a symmetric part to diametrically opposite direction. This part will experience similar kind of force, which is directed like this, dF, and this is also theta. Its component in this direction dF cos theta, and in this direction dF sin theta. All sin theta components cancel each other, and cos theta components addition, vector addition, gives net force. So net force experienced by that entire sphere is the vector addition of cos component of the forces experienced by circular strips. So I am writing the net force experienced by the sphere is integration of dF cos theta. All cos theta components addition gives net force. What is the dF? Write that dF there. dF, this whole term, write constant terms outside. The integration 4 pi I r square by c are the constant terms. Now the terms within the bracket are, here cos square is there, one more cos theta, cos cube theta into sin theta d theta. This is the net force. So if you now here integration of this. So for a simple integration, let us treat cos theta is equal to z. This is z. Now for d theta, differentiate this on both sides. Differentiation of this minus sin theta d theta equal to dz. Substitute these two here. The net force is 4 pi I r square by c. So this is what, z cube sin theta d theta is what, minus dz. So here that integration of that will be, write all the constant terms as it is outside the integration, 4 pi I r square by c. That integration of z cube dz is z power 4 by 4 and minus this 4 cancelled. So I pi r square by c. What is z? That cos theta minus cos theta power 4, limits for theta. You can see here circular elements will be started from here to here. For this element, what is the angle here? This angle theta for this small element located at this front edge. So that is 0. Now for this element here plus pi by 2. These elements are distributed from here to here only. That radiation is eliminated up to here, not this back side of the sphere. So limits of that theta 0 to pi by 2. Now apply the limits. You will have I pi r square by c, upper limit cos 90 is 0 and lower limit that is 1. So directly you will have this, that is 1 after application of limits. So therefore force experienced by this perfect reflecting sphere due to radiation is I into pi r square by c. The same thing we got for perfect absorbing sphere. For perfect absorbing sphere also we got I into pi r square by c. From that you can understand the force, radiation force experienced by the sphere is independent of nature of the sphere, whether it is made with perfect absorbing material or reflecting material. It experiences same force, which is I radiation intensity into pi r square by c. Clear?